Hi, my name is Mehdi. I'm going to present BERT-Sort, which is a zero-shot MLM semantic encoder on Ordinal feature for AutoMLs. This is a joint work with VPaint, Lay, and Moku. When we submit the tabular data to AutoML tools, sometimes those features include the ordinal features, which means the semantic between the values is important, and we want to capture those semantic. However, when we submit those values, regularly AutoML tools and data scientists, they use the function like an ordinal encoder, categorical encoder, which purely rely on alphabetic sort and sort those values and then assign the integer value to each unique value. That's how encoding value works in these functions. However, when we look at this ordinal features, we expect that to have some semantic order, which is expectation completely different than alphabetically sort values. There is some approach that we can tackle by using, for example, label data to understand the semantic orders. For instance, in this paper, you can find how train a model to understand the severity of the cancer from leukemia to melanoma. However, without having the label data, what we can do, how we can process and generate these orders. So if we look at the different contexts, like a mild, moderate, and severe, it could appear in different contexts, in different words, different Wikipedia articles. And regularly, we can use the language model because language model can understand the number of the words before and after a target word, and we can see what's the probability of appearance of each specific word. For instance, how likely severe appear before moderate or after moderate. So then we can capture based on this probability and understand. We can use the BERT. BERT is a pre-trained language model. They use a large number of the corpus, like a book corpus, Wikipedia, and they regularly use the fine-tuning approach for downstream tasks. But we want to remove this fine-tuning and use the zero-shot setting. So this is how BERT-Sort works. First, we look at the data set, tabular data, we generate the unique values. Once we generate the unique values, we then select the different pattern cases, all those possibility of the appearance of the values in the different orders, which is we call it pattern cases that include C1, C2, C3, etc. And then we mask each element for each CI. So then we're going to generate, for example, for the C1, 12 different mask element, and then we're going to submit this mask element and pattern elements to the MLL or pre-trained language models. Once we submit that, we generate the probability of the mask element. If we generate the summation of this mask element, then we're going to produce the probability of each case, which means, for example, provide the C1, what would be the probability, and what would be the probability for the case number 2, pattern case number 2, and etc. So then when we look at the highest case probability, in this case we have a C3, then we're going to generate the best possible semantic order, and we can encode those values and assign integer to each values. That's how BERT-Sort assign and encode the values. So, but there is a problem. When we have the large number, for example, let's say 12 unique values, then we have to generate 12 factorial pattern cases. In order to reduce the number, we select a acceleration algorithm that generate first, for example, let's say select 5 elements, sort 5 elements from those 12 elements. And then once we sort those elements, then we're going to add sequentially one by one each element between those sorted 5 elements. So in this case, we have the October, then we're going to add October. For example, October appear in the first, October appear in second position, third position, etc. Similarly, we can use the BERT-Sort to sort these 6 cases. And once we find the best cases, then we're going to add the next element, for example, add May. And similarly, we can do the process for the other rest of the elements. And finally, we can get sort of all elements eventually. In order to evaluate our proposed approach, we use 10 publicly available dataset and 42 different features that listed in our GitHub repository. We use 2 different approaches to sort elements, and we compare it against the Ordinal encoders to see what the semantic evaluation would be, how much effort we have BERT-Sort that improve or reduce the performance, as well as how might be effective in using the different approach. In addition to the BERT-Sort, we can have in ultimate AutoML platform improve the performance of the model when we train and use the encoded value. So we generate the one approach we use the evaluation ordinal accuracy that punish if there is a, for example, January, February, only one distance to actual value, then it's going to have a better performance in compared to rank value. For example, other March and January, they have a 2 a position away from the actual value, so then it's going to punish that one by using this ordinal accuracy. We also have captured the accuracy metric, and we use 4 different pre-trained language model. As we can see, this is the ordinal encoder performance, and as well as we can see the BERT-Sort by using 4 different pre-trained language model. As you can see, this is in this table. We have the M1 that has a performance with 20 percentage improvement gain in compared to the ordinal accuracy. We also did some experiment how to generate the context, which is explained table 13. We also, for AutoML evaluation, we use the 5 different transformation. One is original, and then a human annotation, encoded BERT, and then we use the sentence BERT and reduce the number of dimension to 1, use the PCA and ordinal encoder, and finally BERT-Sort. And then we use 4 different shuffle data and see on 4 different AutoML platform capture the F1 and accuracy. So as shown in this table, BERT-Sort perform very well close to the human annotation, as a data scientist might encode manually those values and provide better performance. But as you can see, ordinal encoder in general is actually reduce the F1 and accuracy score for models in ultimate models. This is the detail of the 4 different AutoML, AutoGLON, FLAM, H2O, and MLJAR, as well as we did performance evaluation on BERT-Sort and ordinal encoder on 11 algorithm on single data set that shows all the value BERT-Sort provide better performance in compared to ordinal encoder. We also perform some multilingual, multi-domain BERT-Sort. As you can see on this table, it shows the, for instance, we submit the leukemia, cancer, melanoma, which is very domain specific, use the Roberta large, but just by replacing to bioclinical BERT, we will be able to sort the elements. Similarly, we can do sort elements in Japanese, Spanish, Chinese. We also recognize the confusion when we have the graduation in different position with almost close score, as well as we can see some example associate professor, assistant professor, and professor sorted elements. We can also sort elements, for example, fast, slow, normal. Now we can sort element first, fourth, second, 7, as well as we can see the 3rd element is not up here, but it's the BERT-Sort successfully sort element. Even it can go further and sort element like RGB and recognize what the best semantic order would be, or good, excellent, fair, outstanding. We can sort element. In conclusion, we introduce the BERT-Sort, which is a 0-shot setting, no fine-tuning, no pre-training, no retrain the model. So the model will be able to, in 0-shot setting, provide this type of performance, as well as we generate the benchmark that include 10 public data sets with 42 different ordinal feature, and we have 22% performance gain. Feel free to contact me by email, as well as look forward to meeting you during the conference. Thank you for your attention.